Okay, so here we have paper 2, simple harmonic motion. It says it's 148 marks. It's not. It's 148 marks altogether, including the old SL and AHL material that we haven't even gotten to yet. And I just want to focus on the parts that are simple harmonic motion, so there's a lot of this that I'm going to skip. I could do the SL material as a review, but right now I just want to focus on SHM so we can get the ball rolling in topic 9. All right, we have some questions here. First off, we have a setup where we have two equal point charges of 44 positive 44 microcoulombs and a point P that's it's a distance away. It's important to note that they're both positive charges. And so we have 1C for 2 marks. Why will Q perform SHM when it is released? Also notice that point P is moved closer to the charges, but that's not really going to matter. So SHM has 2 conditions. So the first condition of simple harmonic motion is that it's proportional to displacement. And I can see that that's given here in the description of the problem, that the force is approximately 115 times the displacement. So if force is directly proportional to displacement, then acceleration will be too, because force is directly proportional to acceleration, of course, by F equals ma. Now, the second condition of SHM is that the acceleration is negative the displacement. That doesn't say that in this expression that I underlined earlier. However, it does say that the point charge Q is placed at point P, and that point charge Q is negative 2 microcoulombs. And we said earlier that these two charges are both positive, and so if they're positive and the point charge is negative, then it will attract. So it's for a positive displacement. We have the original, it's saying that the point P has a positive displacement in the up direction, but those charges are going to pull back on it. So that force is going to be a restoring force back towards the equilibrium position. It does say explain, so we'll need to say why that's true. So yeah, the point charge is negative, both of the Q and Q are positive, opposite charge signs attract, so the force opposes the displacement, and if the force is negative the displacement, so is the acceleration, again because F equals ma. And based on the mark scheme, that is sufficient. Okay, so calculate the period of oscillations of Q. We know that the period, or rather omega, is 2 pi over the period, so period is 2 pi over omega. We also know that acceleration is omega squared x. We also know that by Newton's second law, A is F over m, and the problem tells us that F is 115 times the displacement, and we're also given a mass of 0.25 kilograms. So I can take the A equals omega squared x, and A equals radical as sum of the net force over the mass, set them equal to each other. So then I have omega squared x equals the force over the mass, so it would be 115x over m. The x's, the displacements, cancel from both sides. So I have omega squared is 115 over 0.25. Square root both sides, I get that the angular speed, omega, is 21.4476, etc. I take that back to t equals 2 pi over omega, and then solve for that period, and it's 0.29 seconds. My original number of 0.25 kilograms, that's 2 significant figures, so my answer will have 2 significant figures. What are the 2 marks? I believe 1 mark is for the answer, of course, and then the other mark is for for the 2 equations, but really there are 3 equations that were used here. Omega equals 2 pi over the period, A equals omega squared x, and A equals F over m. So, I don't know, somewhere it's awarding 1 point for kind of 2 items, but anyway, that's 1D. This particular slide has no simple harmonic motion on it. But here we go, simple harmonic oscillations, 2B. Alright, so here's another simple harmonic oscillation situation. We have frequency, we have amplitude, and we want to know what the maximum speed, show that the maximum speed is 20 meters per second. So we're going to have to do a conversion at some point from centimeters to meters. You know what? Let's do it now. Forget about this centimeter nonsense. 8 centimeters, 0.08 meters. There we go. So we're talking amplitude here, we're not talking time, so we're going to need a formula for speed as a function of position, not as a function of time. Let's go to the data booklet. All right, so here's that equation that relates speed to displacement. And now it says maximum speed is 20 meters per second. Well, where does the maximum speed occur? That occurs not at the amplitude, because that's at the amplitude at the max displacement, the speed is 0, but rather at the equilibrium position, that's where the speed is a maximum. That's for both simple pendulum and mass spring. So at the equilibrium position, we say that the displacement is 0. And so if the displacement is 0, then we just have radical amplitude squared, which just, of course, leads us just to the amplitude. So the maximum velocity is plus or minus the angular frequency times the amplitude. So we have the amplitude, but we need to figure out the angular frequency. Now, we're not given the angular frequency, we're given the standard frequency, but you can relate standard frequency to angular frequency. We know that omega is 2 pi over the period, and that we remember, let's see, is that t equals 1 over f and f equals 1 over t? Yeah, there it is, in subtopic 4.1, t equals 1 over f. So that gives us, so if t equals 1 over f, then f equals 1 over t, and so omega is 2 pi times the frequency as well. I'm going to sub that back into Vmax. And we're talking speed here, so I'm not concerned about the negative solution. I'm just going to say, I'm going to drop the plus or minus. And that leaves us with a maximum speed of 20 meters per second when you round for significant figures, and our first two numbers, the 39 and the 8.0, are to 2 sig figs. And there you have it. The 2 points are for showing the equation, and that's the first point, and the second point is for the correct answer. Doing the math right, I guess? Okay, our next SHM question is number 3C, so let's go there. All right, so here is number 3. We have a guitar, and so there's a number of things about this guitar. It's also about standing waves. It says that the string vibrates with simple harmonic motion, but 3b is merely more of a v equals f lambda question. It's not an SHM question. And it does say that the string is vibrating in simple harmonic motion. So that is the case. And so it says, all right, so sketch a graph to show acceleration versus displacement. Aha, well, we have simple harmonic motion, so let's recall. There's the defining condition of simple harmonic motion. The acceleration is directly proportional to the displacement, and the acceleration is negative the displacement. So what does that graph look like? It doesn't specifically have to have that slope, but the slope needs to be linear, and the slope needs to be negative. Oh, and it needs to pass through the origin. So that's actually 3 conditions for 1 mark. But, I mean, it's a simple graph, so just remember that graph. 3D is also an SHM question. 3D is on the next page. Found it. The string is displaced 0.4 centimeters at point P to sound the guitar. That's going to be the amplitude. 0.4 centimeters. Well, question says 0.4 centimeters. That is one significant, that displacement, one significant figure. I don't really know why they did that. 3D here is just like, what's the problem we just did before? Yeah, so 3D has the same breakdown as 2B. We're looking for the maximum velocity of a point, and they give the regular frequency. But again, let's walk through that real quick. Incidentally, they say velocity here. They actually mean the magnitude of the velocity. They're looking for the speed. We saw from 2B that omega is 2 pi times the frequency, so we have everything we need. I need the amplitude. Let me go back to the beginning of the question. And of course, be careful, don't make the boo-boo that I almost just made. It's not 4 centimeters, it's meters. So that would be 0.004 meters. And I'm converting to meters because the speed that I'm looking for is in meters per second, not centimeters per second. That's why I'm converting from centimeters to meters. All right, let's calculate. And we get a max speed of 4.9 meters per second. Now, That's what the mark scheme says, but the here. So honestly, the answer really should be just simply 5 meters per second. So I'm going to write both. In my opinion, that's what the answer should be because they only chose to give. 3E is another SHM question, and what's the acceleration of this vibrating point P? So the acceleration, I think it wants the magnitude, the amount of the acceleration, so I'm not really concerned about the negative. But I'm going to say that A is omega squared times x. And of course, the maximum acceleration happens when the when the displacement is at a maximum because acceleration and displacement are directly proportional. So we get a pretty hefty acceleration, 6,000 meters per second squared, and if we divide that by g, which is 10 meters per second squared, we get that the maximum acceleration of that point on the string is 600 times the acceleration due to gravity. That's why when you look at a guitar string, your eyes can't actually like see it vibrating back and forth. It's so fast and the acceleration is so high. And the 2 points are for the equation, 1 and for the answer. And we have another SHM question. Estimate the displacement needed to double the energy of the string. Well, the energy of a simple harmonic oscillating system is 1/2 times the mass times the angular speed squared times the amplitude squared. So it's asking about that displacement, or rather the total energy is dependent upon the amplitude. So really kind of like how would I need to adjust the amplitude so that I could double the energy. So I'm looking for the amplitude here. So I want to solve for the amplitude. And so we got that the amplitude is radical 2 times the energy over m omega squared, or rather that the amplitude is proportional to the square root of the total energy. So it said it wanted to double the energy. So if I go to double the energy, then that is what's going to have to happen to my amplitude. So the displacement needed is going to be radical to whatever the original displacement was. So if the original amplitude of the string was 0.4 meters, in order to double the energy, I would need an amplitude of 0.6 meters. 2 points here, 1 for the equations, and the other for the answer. Let's see, what else we got? So 4A, it says, why does the cylinder produce simple harmonic motion? 4A is an SHM question. Let's go to it. Okay, so here we have this setup where we have a cylinder in water, and without reading the entire problem, you can read it. We do see that the force, the vertical force on the cylinder is related to displacement as negative the density times the cross-sectional area times the acceleration due to gravity times the displacement. Why does the cylinder perform SHM? Well, we know that the defining conditions of SHM are the acceleration is proportional to the displacement and the acceleration is negative the displacement. And that's because acceleration is negative omega squared x, where omega is the angular speed. And so we have this formula over here. I'm going to write outside of the box for a little bit just to explain it. We have the formula that they give us, and I see that the force is directly proportional to the displacement, and I also see that the force is negative relative to displacement. That's as good, proportionally speaking, as saying that the same is true of the acceleration, because F equals ma, and so therefore F is proportional to a. So if F is proportional to x, then a is also proportional to x. That would be a ding for simple harmonic motion. Also, I see that the force is negative relative to displacement, and since force and acceleration are directly proportional, the acceleration is also ding negative to the relative to displacement, and so there we are. It satisfies the conditions for simple harmonic motion. Next question. Let's see. It is not on this page. Let's proceed. So we're given the mass, we're given the cross-sectional area, we're given the density of water, and it says find that the angular frequency or angular speed is about 4.4 radians per second. which, considering that we operate in radians, is just fine. Well, the force equation given by the problem is that F is negative density times cross-sectional area times acceleration due to gravity times displacement. We need a few other formulas. All right, so we have A is F over m, and A is also equal to negative omega squared x. So here's what that is going to do for us. A is F over m, so that I restrict the formula for force, and I just put that over m. A is also equal to negative omega squared x, and it's asking us to solve for omega, so let's clean this up a little bit. So we get that omega squared is rho ag over m, and we know rho, we know a, we know m, and g, of course, is, we can probably approximate that as 10, so let's substitute and solve. I feel like they don't really give you a lot of room. All right, let's squeeze a little. So I subbed in the density, I subbed in the cross-sectional area, that's density of water. Cross-sectional area, I subbed in g, and I subbed in the mass. Let's see what we get. This was a little unexpected, and I'm going to correct it, but I found that the IB usually allows 10 for the acceleration due to gravity, but the mark scheme specifies 9.81, and it's going to matter in the solution. And so it is 9.81, so let's use 9.81 there, because when I use 10, I get 4.5 as an answer. Hold on, let me check for sig figs. We have 3 sig figs, so yeah, I get 4.47 as a solution, which rounds to 4.5. However, when you use 9.81, you get 4.43. We wind up with 4.43 radians per second. Radians, of course, is not really a unit. It's really just seconds to the negative 1. I just want to explore for 1 sec resolving the units. So here's a fun little exercise. We have density as kilograms per cubic meter. We have area in meters squared. We have acceleration due to gravity in meters per second squared. All of that divided by mass. So I said times kilograms to the negative 1. All of that is then square rooted. Let's see what we get. So first and foremost, kilograms times kilograms to the negative 1 cancels out kilograms. Meters to the negative 3 times meters squared times meters cancels out all of the meters. And we're left with radical seconds to the negative 2, which of course resolves as seconds to the negative 1. So yeah, and then it's radians per second, because honestly, both radians and degrees are just pretty much a placeholder. We know that both frequency and angular frequency have units of seconds to the negative 1, essentially, in terms of fundamental SI units. The mark scheme didn't require you to resolve the units, but I just wanted to do it just to show you, because it's important to see. And here we have for C, they want the maximum kinetic energy of the cylinder. If the cylinder is oscillating as a simple harmonic oscillator without any damping or friction forces, the maximum kinetic energy is the maximum potential energy is the total energy. So we don't really even need to use the kinetic energy equation, we can use the total energy equation. This is when the mark scheme gets a little bit Bose-X. Mark scheme says the answer is 71.4 joules, but they're also using 4.4 for the angular frequency. Yet in 4b, they said that the solution needs to be at least 3 significant figures. That's why I wrote 4.43. So I don't know why they're suddenly using 2 significant figures in 4c. Like I said, that's the Bose-X. So I'm going to use 4.43, I'm going to get 72.4 joules, and I'm going to declare myself correct over the mark scheme. I mean, I kid, of course. You can be like, you can't just say that you're smarter than the mark scheme. I'm not saying that. But I am saying that all of these values are legit. The mass is 118 kilograms. The angular speed we got earlier from 4b is 4.43 radians per second. I put that in for omega, and the amplitude was given right here. X is 0.25, so I slipped that in. Don't forget to square, by the way. Most common careless mistake, forgetting to square. I wind up with 72.4. I round for 3 significant figures, 72.4 joules. And then 4D wants a graph of kinetic energy versus time. Well, I know that at the initial condition, this is the Cylinder is pushed down 0.25 meters, so I'm at max displacement. I'm at the amplitude condition, and where the amplitude can, where I'm at, where when your displacement is at the amplitude condition, at the starting point where of max amplitude, we have no speed there. And if there's no speed there, then we must be starting at the origin. That's important. And then realize we're talking about one full period, one full oscillation. And again, so if we're talking about like a simple pendulum, one oscillation would start from maximum displacement, would swing through and then go to the other side. That would be halfway through the cycle. So the speed on the other side is also zero. So halfway through the oscillation, the energy is going to be zero, and then it's going to swing back. And then once it finishes its oscillation, its speed again is going to be zero. So that's the end of our oscillation. Energy, of course, is never negative, so we're not going to use the bottom portion of this graph. And we know that the energy follows not it doesn't follow like a sawtooth graph. We're not doing like that. That's not going to do it either, although that would approximate what's happening, right? We have, 1/4 of the way through the cycle is when the pendulum passes through its lowest point and its fastest point, so that's when the kinetic energy would be at a maximum, but it doesn't follow the sawtooth pattern. Instead, it's going to follow kind of like a sine curve pattern with maxima, and actually I should mark off we have a maximum in these points right here, so let's try and be as curvy as possible without making what the IB likes to call a hairy line. My artistry astounds. Not quite, but close enough. If you're wondering what the 2 points are for, it's not for the two curves, it's the fact that we have the right shape, and also that there's nothing in the negative. That's it for this slide. Let's check the next one. That next one would be a new question. So now we have question 5. And again, the numbering of these questions is done by QBank. They're just pulling questions from old IB exams, but they are legit IB questions. All right, so we have a graph of kinetic energy versus time, and we want to know the length of the thread of a simple pendulum. So the length is featured in the equation. T equals 2 pi radical L over G, so if we solve for L would be the period over 2 pi all squared times G, which 2 pi, of course, is a constant, G is a constant, but we need to figure out the period. So let's take a look at this graph. Now, the graph is versus time, and it shows a simple harmonic oscillator cycling with its kinetic energy. So we have to think about where is the kinetic energy a maximum and where is it a minimum. And by minimum, I mean 0. What's interesting is that the problem setup says that a pendulum bob is suspended at rest from a fixed point, and then it's released, and it says the pendulum begins to oscillate. Now, if the pendulum bob was suspended at rest, the kinetic energy would be 0. But I can see from this graph that the kinetic energy is starting at a maximum of 20 millijoules. So they're starting time 0, not when they release the pendulum. They're starting time 0 actually when the pendulum reaches its lowest point, its equilibrium condition. So remembering that the kinetic energy is a maximum when x equals 0, so here at time 0, the kinetic energy is a maximum of 20 millijoules, and then it returns to 20 millijoules right here. All right, so then basically we have it's going fastest, and then it swings up to its highest point right here where the kinetic energy is 0, and then it swings back through the equilibrium position at about 1.125 seconds roughly. That's right here, and then it reaches its other apex point, other amplitude point right here, and then it swings back down to the equilibrium position, completing one full cycle right here at 2.25 seconds. So that would be the period. Using 9.81 for G, because they were picky about that before. Also dropping my calculator for extra special effects. We get 1.26 meters for the length of the pendulum. Be careful, I just made an error where I did 2.25 divided by 2 pi. I forgot to put the 2 pi in parentheses. So then the calculator will do 2.25 divided by 2 times pi. So just be careful when putting your numbers into your calculator. But at any rate, 1.26 meters, and it agrees with the mark scheme. My original numbers were all to 3 significant figures. My period was to 3 significant figures, and so therefore my answer will also be 3 significant figures. 3 marks. The first mark is for identifying the period as 2.25 seconds. 1. The second mark is for second mark is for the answer, and the third mark is actually for the unit. So yeah, it's length in meters. So there you go. All right, there's 5A. Let's move on to look at the graph. And we notice that the graph is of kinetic energy versus time. So we can use kinetic energy to also talk about the speed, remembering that we can see that the kinetic energy, when the initial speed, that would be when time equals 0, when we're starting with, the kinetic energy is at a maximum. And so therefore the initial speed must be at a maximum. And so we're using the y-axis to try and figure this out instead of the x-axis, because with proportional changes in the velocity, I can figure out the resulting proportional change in the kinetic energy. Right there on the graph. See that from the graph that at the highest point, the kinetic energy is 20 millijoules. There. 5B on the next page over here says label on the graph with the letter x, a point where the speed is of the pendulum is half that of its initial speed. Kinetic energy is 1/2 mv squared. So even though we're talking about speed in the problem, the graph is one of energy. So the question says that where the speed is 1/2 that of its initial speed. Let's look at the graph again. So we're starting with v being in its maximum value, but then it wants to know, basically label on the graph with the letter x a point where the speed is 1/2 that the initial speed. We're going to be looking for, where's the kinetic energy? We're basically, hold on, let's go back to the graph. So here's what I mean by that. Obviously, kinetic energy is proportional to v squared, and so I'm looking for, where is the kinetic energy when v is half what it was to start? And so if you square the velocity, that is 1/4 the kinetic energy. So basically, we're looking for a point on the graph where the kinetic energy is 1/4 what it is to start. And so the original starting energy was 20 millijoules. And so if the starting kinetic energy is 20 millijoules, 1/4 that kinetic energy is 5 millijoules. So where on the graph? I'm not sure that 5C is simple harmonic motion, because it doesn't really, the equation we're going to be using is for kinetic energy. We don't know the displacement and we don't know the amplitude. However, we do know the kinetic energy, the maximum kinetic energy of the bob, and we do know that kinetic energy is 1/2 mv squared, and that's not really a super complicated formula. So I'm gonna do this guy anyway, but I don't know that it would be included in topic 9 per se, but since we're talking about kinetic energy, we can still do this. This would be an energy issue. This is topic 2.3. But our equation is, of course, kinetic energy is 1/2 mv squared. And we're talking about V max. And so we know that the maximum kinetic energy happens where the maximum velocity happens, and we know the maximum kinetic energy, and the maximum kinetic energy is 20 millijoules. And so we want to get back to standard units, so instead of millijoules, that's 10 to the negative 3 joules, and instead of grams, we need kilograms, so that's 0.075 kilograms. And so the energy taken off the graph is 2 sig figs, the mass is 2 sig figs, so my answer would be 2 sig figs, but yeah, 0.73 meters per second is close to 0.7 meters per second, so there you go. And the 2 points are for the answer and for the units. I think the shown work and the answer, and then also then the units. So there you have it. But again, like I said, I do not think that this is simple harmonic motion. I think it's topic 2.3. That's interesting. I'm looking at the mark scheme, and it says that you need two significant figures in order to get 2 points. So I actually am correct in saying 0.73. Now I think there is one additional SHM component from this multi-part question, and it's not D, but it's actually going to use 5D. 5D is an inelastic collision problem. We're going to need to figure out the speed of these combined masses immediately after the collision, which of course is a collision problem and we find it in the data booklet. So yeah, this would be topic 2.4, and strangely, neither the Regents reference table nor the IB data booklet includes the equations for collisions. I really don't know why that is, but let's figure that out. I can show you the equation if you don't recall it. Oh, and I keep on using V. Well, yeah, V. Yeah, okay. I mean, I forgot that. Like, you don't say initial and final. You say U. V initial is V. And I have to, hold on, let me look that up. Yeah, V initial is U, V final is V. But I'm not sure that applies here. All right, so then I'm still good. And so there's 5D. We have the combined mass when they stick together. Their velocity is 0.4 meters per second. Now, why is that important? Because we can get the energy after the collision. We're going to need that for our graph. And they said that the Bob is moving at 0.8 meters per second when you actually do. But it's 5F, sketching the graph of potential energy versus time. And so the potential energy graph is going to be the inverse of the upside down, inverted graph of kinetic energy versus time. But in order to draw the correct amplitude, we're going to need to figure out how much energy does the system have after the collision. So really, in order to do this graph, we're going to, and this is kind of annoying, the initial kinetic energy is not 20 millijoules the way it was in the graph. The initial kinetic energy is actually 24 millijoules when you actually figure, I guess they thought they would get cute. Half mv squared using the mass of the bob and 0.8 meters per second, you get an energy of 24 millijoules, not 20. That was the original graph. And there's actually something, blah 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 blah. Yeah, there's an issue with the mark scheme on this, but we'll get to that. Then I need to figure out after the collision what's the energy of the combined the two metal balls together, so I can do 1/2 mv squared with the combined bobs, I guess you could say. Alright, so the whole point of figuring out the initial and final kinetic energy is to show that as a result of the collision, half the energy is lost. It's an inelastic collision. Why does that matter? Because if the original graph, which is already traced out for us in kinetic energy, this was the original, wow, that's terrible. This is the original graph, that's still kind of terrible, but you see where it is. Then the potential energy is the inverse of the kinetic energy. So the potential energy would be, start down here and kind of go like that, but it has to have half the amplitude, so it would not be that high. And there's the graph. You have to excuse my shaky line. I'm trying not to rest my palm on the iPad itself, so I'm kind of painting this thing from a distance, but there you have it. The 2 points, 1 point is for inverting the graph, showing that the potential energy is the inverse of the kinetic energy. The other is for the smaller amplitude, that it's smaller there. This whole bit right here, I don't know why they included this whole writing section. They did not need anything in there. I used it to explain my answer for you, but I don't know why that was there. Okay, so our next bunch of questions. This is a Doppler question. That's not. We're not doing that yet. So the next bunch of questions involves a climbing rope being tested by having a mass attached to it, and then you release the mass and it stretches the rope. So a lot of these questions do not gauge. I believe, is it here? There it is. Again, you have to read through this stuff carefully, but the mass of the block is 80 kilograms. All right, so then we can use that mass with SHM. Let's see, those, not here on this page, don't. Those bit. And let's see, not here on this page, don't. But here, 6H, calculate the time taken for the block to return to the equilibrium position, assuming that this mass spring, elastic rope would be a spring, assuming that this mass spring system undergoes simple harmonic motion. I didn't actually see that, but the mark scheme approaches it as if it were an SHM question. So I guess, I mean, it is a mass spring system, and it uses the mass spring equation for period. So, all right, we're going to go with it. But I feel like elastic ropes, they work under tension. They don't work as great compression springs, but I don't know, whatever. I think I'm overthinking this. All right, so 6H, let's proceed. I need black ink. All right, so just as a comment, first of all, the time from the maximum displacement from the amplitude position to the equilibrium point where x equals 0, that's 1/4 of a total cycle when we're talking SHM. Like if we're talking cosine curve, the equilibrium position would kind of be like here. These would be the max displacement points. So to go from the max displacement to the equilibrium position is 1/4 of that full cycle. Why does that matter? Well, the time that they're looking for is 1/4 of the period. So really, if I need to go and solve for the period, and the period is 2 pi radical m over k. We have the spring constant. It's 400 newtons per meter that was given to us, but we need the mass, which is not given to us above this problem. We have to go back a little. And so, yeah, we do 2 pi radical m over k, 80 over 400. Again, the spring constant is right there. But we get 2.81 seconds, and 1/4 of that is 0.702 seconds, and that is our answer. Okay, now we need the speed as the block passes through the equilibrium position. So we have our speed versus position equation. And if we're passing through equilibrium, that means our x value is 0. And so let's say equilibrium, x is equal to 0. Therefore, the speed, and we're talking speed, so there's no minus, equals omega x naught. All right, so the amplitude is actually given up here. The block is pulled 3.5 meters vertically below the equilibrium position. So that would be that's where the 3.5 is coming from. And omega is 2 pi over the period, and then the period, of course, is over here. Right, we solve for the period. And so period goes in, we solve for omega. I get 2.23601, etc. I slip that in for omega on v equals omega x naught, and I get 7.83 meters per second. The mark scheme says 7.84, but they rounded in the intermediate step. They rounded the 2.23601, blah, blah, blah. So I am calling them out on a rounding error, ew. But not really a big deal. We're only off by like 100th. So yeah, that's a 2-point question, 1 for the answer. And let's see. Yeah, it's, I guess the 2 points, one of them is determining the omega, and then I think the other one is for the answer, perhaps. Another way of solving this question involves a conservation of energy treatment where 1/2 kx squared for spring potential energy equals 1/2 mv squared for kinetic energy, where you can slip in the spring constant, the stretch, the 3.5 meters for x, you can put in the mass and then solve for v, you end up with the same answer. But that's not an SHM solution. So anyway, there's 6I. Okay, let's keep going. So now we have a ball that is rolling in a bowl. And so there's a bunch of questions about the bowl system. Say that 10 seconds fast. And we think radius of the bowl. Here it is. Radius of the bowl is 8 meters. So then we know that the force, and here is where the SHM comes in on 7F. So now they changed the system so that we just have we're looking at a side view cutaway of the bowl. That's right here. Oops, I'm using an eraser, not a pencil. That's the side view cutaway of the bowl. And it says that the ball is released given a certain amplitude, I suppose, and is then rolls down back towards the equilibrium position. And it says the magnitude of the force on the ball is given by this expression here. Now, this is a 1 mark question, so even though there are 2 conditions for simple harmonic motion, the one that they're really looking for is the fact that the force is directly proportional to the displacement. And since, of course, F equals ma, then if the force is directly proportional to displacement, then the acceleration is as well. So you could reason out that the ball will also roll back towards the equilibrium, roll down the side of the bowl towards the equilibrium position, meaning that the force is also restorative back towards equilibrium, but that's not expressed in the formula. They refer to the magnitude of the force, in fact, so they are avoiding that on purpose for some reason, but it's a 1 point question, so what we said is enough. Let's see. Yeah, it's over there, radius of the bowl. Was the value for R. It says that some. Okay, so we have, let's see, 7G. Show the period of the oscillation is about 6 seconds. So period is related to angular frequency by omega is 2 pi over the period. Therefore, period is 2 pi over omega. Okay, fine. Well, can we figure out what omega is? Well, we know from SHM that omega is, acceleration is omega squared times x, and acceleration is also F over m because of Newton's second law. We were given an expression for force, being F is mgx over r, where r is the radius of the bowl, and x is the displacement away from the equilibrium position like we do in SHM. So if we collect like terms, if we, let's see, substitute the F for A equals F over m, substitute that expression for F, we eliminate the mass, so we get that the acceleration is gx over r, and then I take that acceleration for gx over r, and I bring this guy here, and I bring that back into my formula for A equals omega squared x. And so that's where I'm right here. I set them equal to each other. Omega squared x is equal to gx over r. The x cancels. I solve for omega, square rooting both sides. Omega is radical g over r. Acceleration due to gravity divided by the radius of the bowl. So now that I know that, now that I've solved for omega, I can bring that back to the period, because remember that the period up here, right, has omega in it, so that's why we solved for omega. And so I bring that radical g over r in for omega, and I get that the period is 2 pi over radical g over r. I slip in 9.81 for g. I slip in 8 because it was 8 meters. Where? And I solve it all out. 2 pi divided by radical 9.81 divided by 8, and I get a period of 5.7 seconds, which is about 6 seconds. And 5.7 agrees with the mark scheme. Okay, here we have 7H, and we need to draw a graph of velocity versus time. They give us the amplitude, and they say draw a graph to show variation with time of the velocity v during one period. Well, we just figured out the period in 7G as 5.7 seconds. The mark scheme says you can use 6 seconds for the period, which is convenient because these, I guess if we zoom in, we can make use of it. We can complete the cycle in 5.7 seconds. I suppose that's really kind of annoying, but It's the question really is, what the heck are we supposed to do with that amplitude of 0.12 meters? Yeah, so that's a thing, and let's discuss. So it's like, why are they giving us the amplitude? Well, knowing the amplitude, we can actually solve for the maximum velocity. And that's not going to be within the box, but I'm going to kind of explore that right underneath the box. And yes, I realize that the graph is velocity versus time, and what I just wrote is velocity versus position, but I'm trying to make use of the amplitude being 0.12 meters as it applies to the velocity, because that's going to give me the amplitude of the curve that I will draw for velocity versus time. I want to know what is the maximum velocity of the system. Well, we know the maximum velocity of the system occurs when the displacement is 0. So if x equals 0, then the maximum velocity is, and again, right now I'm looking for the amplitude, the maximum value of velocity, both positive and negative, so I'm not so much concerned about the positive, negative. In fact, my curve will both have a positive velocity and a negative velocity in representing one cycle. Of course, omega is 2 pi over the period, and we know what the period is. We're going to need to know what the period is in order to draw one cycle, but it also applies to figuring out what the heck V max is for figuring out what the amplitude of the curve that we're going to draw is. So let's throw some numbers in and see what V max is. Working the numbers through, that gives us a maximum velocity of 0.13 meters per second. Okay, so now that we know the maximum velocity, which would be the amplitude of this particular curve of velocity versus time, we also know the period of 5.7 seconds, which is the time to complete one cycle. Since I have the luxury of looking at the mark scheme, I can actually draw the curve with the accurate maximum displacement points and 0 displacement points. But it does say in the mark scheme that if you use 6 seconds to represent one cycle, they'll take that. I feel like that would make the curve a lot easier to sketch. Let me show you the 6-second period curve, and then I'll draw the actual curve, but either one is acceptable. So first I'm going to draw where the amplitude should be, and it's 0.13 meters per second. So that should go right around here. And then down on the negative portion, that should get us right around, oops. Let's do that again by selecting the proper thing. Okay, so let's try that again. Yeah, but here, can I actually take that line and move it? I can move the background, I can't move the line. Good enough. All right, so that represents 0.13 positive and 0.13 negative, and then let's actually draw the curve. We said that ending the curve at 6 seconds is acceptable. That means that halfway through the curve would be 3 seconds, and 1.5 seconds would be the point of maximum amplitude, so let's find that up here. And then we have, let's see, 4.5 seconds would be for negative maximum displacement. That would be right here. And so the curve would look a little bit something like that if you were to say that the period were 6 seconds. But the actual second period is 5.7 seconds, so let's actually give that a go. Get a nice fat zoom going on. We end at 5.7 seconds. That means that the halfway point would be 2.85. There's the halfway point, and then the quarter points would be a smidge over 1.4, 3/4 of the way through, a bit more than 4.2. So here's how the curve, those are the most important points, and then you just try to connect them to make a sinusoidal curve. Not too bad. I mean, through the middle point, I missed a little tiny bit, but I think that's pretty darn close. I also have the luxury of being able to zoom the page. Well, the mark scheme is actually telling me that that should be inverted. From time zero, we actually wind up with a negative velocity to begin with, and then we wind up with a positive velocity. But it says except either. I put some effort into that sine curve, so if they say except either, I'm going to leave it as it is. So there you go. Let's see, 3 marks. What are the 3 marks? The amplitude is correct. Should be some kind of sine shape, and with the correct period. They say 5.7 or 6 seconds for the correct period, which we do have that. And then the last point is that the amplitude should be precise. It also says only one period shown. Maybe that's the third point, that you only draw one cycle. Considering that the period is 5.7 or 6 seconds, I mean, there's not enough space to actually show more than one cycle. So, I don't know. There you go. 3 points. 3 marks, as they say. And there's our graph. I think we're done with number 7 here. Let's move on. Number 8 deals with a satellite in orbit that extends a cable. Of course, that cable is going to be moving in a magnetic field, so that's an interesting proposal. Let's proceed.